Hello everyone. Welcome to your own YouTube channel. ADP for Learning. Today we will learn about the difference between white and brown fats, and we will also see which one is more beneficial to us at which stage of our life. Without taking much time, let's start our session. If I say fats are quite friendly, what will be your response? Maybe you will say, who needs such a friend? Isn't it? Well, actually, we all do need such a friend like fats. Without fats and related molecules, also known collectively as lipids, your body would literally fall apart because there would be no cell membranes to hold it together. As shown in the figure, lipids, including phospholipids and cholesterol, are essential components of our cell membranes. They also serve as raw materials for building specific vitamins and signaling molecules. Not only do lipids form membranes, they are the basis of many chemical messengers and a significant component of nerve cells, forming nearly 60% of the human brain. Cholesterol is a lipid with a bad reputation for its role in cardiovascular disease. Still, it is one of the critical components of cell membranes and the precursor for testosterone, estrogen, and other essential hormones. Fat in food also helps us absorb certain micronutrients, including vitamins A, D, K, and E. These vitamins can dissolve in fat but not in water, and we need a few grams of fat with each meal to absorb them effectively. So a question may arise, what about that extra fat that rounds out our bodies? While obesity isn't healthy, we need some fat tissue. Without it, the balance of hormones and other signaling molecules can be disrupted. There are rare genetic conditions that prevent some people from storing fat, and patients with these conditions often have insulin resistance and other metabolic problems similar to those seen in obesity. Extra fat is even more critical for women because their reproductive health depends on it. It is essential to note that while the body can make some fats, others are essential nutrients. We can't make them, so we have to get them from our food. You will be surprised to know that there are specific chemical signaling pathways that require fat as a significant component, or in the driver's seat. Researchers used to think that fat tissue was inert, serving only to store energy. More recent research has shown that fat plays an active role in regulating many body systems, including the immune system, the cardiovascular system, and the reproductive system. Fat tissue produces more than 50 different kinds of signaling molecules that act on many types of cells throughout the body. The specific chemical signals fat tissue produces depend on both the amount of fat someone has and where that fat is located. In healthy weight people, fat tissue usually produces signaling molecules in the proper or correct proportions. However, having too much or too little fat can disrupt the balance. For instance, inflammation is part of the normal immune response, and fat tissue produces some molecules that increase inflammation and others that suppress it. In obese people, fat tissue makes more pro-inflammatory chemicals, which can raise inflammation to dangerous levels. Fat also helps make steroid hormones, including the sex hormones estrogen and testosterone. Steroid hormones all share a similar structure, and they are produced from scratch in the ovaries, testes, and adrenal glands. Fat tissue can modify these steroid hormones, converting one type into another. Using other hormones as a starting point, fat produces nearly all of the estrogens in older women and up to half of the testosterone in reproductive-aged women. As shown in the figure, you can see fat varies in the types of signaling molecules it produces and in the effects those molecules have on surrounding tissues. For example, fat around the intestines produces higher levels of inflammatory chemicals that contribute to insulin resistance. Also, excess fat in the lower body is not strongly associated with insulin resistance. In general, it carries fewer health risks than fat around the abdomen. At last, you can see fat on women's hips and thighs is thought to be important in fueling the brains of developing infants. Now, the question may arise, what is the famous product of fats? One of fat's most famous products is leptin, a signaling protein that suppresses appetite, increases energy use, and encourages the body to burn fat. In lean people, fat tissue makes low levels of leptin, prompting them to eat and gain weight. As fat tissue grows, it makes more leptin, suppressing hunger and halting weight gain. Leptin levels also go up when people are well-fed, and they drop during fasting or dieting. In this way, leptin encourages the body to maintain a stable weight. When leptin was first discovered in the 1990s, researchers hoped it could be used to treat obesity. Unfortunately, most obese people already produce large amounts of leptin, and their bodies have lost the ability to respond to it, so adding more leptin generally doesn't help. Leptin treatments only work in patients who have rare genetic conditions that keep them from producing leptin naturally. As shown in the figure, you can see mice that cannot make leptin called obese/ob mice are always hungry. They overeat, become incredibly obese, and develop type 2 diabetes. That leads to another prominent question: do you know brown fat? Most of our fat tissue is white fat. It carries out the signaling functions described before, and it stores most of the body's fat molecules. But we also have a small amount of brown fat tissue, which is much more metabolically active. The main function of brown fat is to burn fuel, that is, fat or glucose molecules, to keep the body warm. Infants, rodents, and animals that hibernate, like bears, have large amounts of brown fat tissue. It wasn't until recently that it was also discovered in adult humans. The darker color of brown fat comes from mitochondria, which are present in much higher numbers than in white fat. The mitochondria in brown fat are unique. They contain a protein that mitochondria in other cell types lack, uncoupling protein 1, or UCP1. This protein disrupts, or uncouples, oxidative phosphorylation by moving protons back across the mitochondrial membrane so that they cannot be used for making ATP. Instead, the energy is channeled into heat production. As shown in the figure, you can see in most cell types, ATP synthase shown on the left uses the energy from proton transport to generate ATP. In brown fat, the uncoupling protein 1, or UCP1, shown on the right, uses the energy from proton transport to produce heat. Brown fat has been receiving a lot of attention lately for its ability to burn through calories and improve insulin sensitivity quickly. Researchers are looking for ways to make white fat tissue more brown, or even beige, as a way to control diabetes and help people lose weight. Thank you for joining me on this fantastic journey of learning. We will again meet with new innovative topics. Meanwhile, don't forget to like, share, comment, and subscribe.